Hello. In this video I'm going to be creating a recursive descent parser in Python from scratch without using any libraries for this language here. What is this language? This language is something I just invented. It's called MyLang apparently, and it's pretty weird. The reason that it is pretty weird is because I want it to be very easy to tokenize. What's tokenizing? Tokenizing is the first part of parsing. So we're splitting the program basically into words which are convenient for the recursive descent parser we'll be seeing later on. What's parsing? The goal of parsing is to take the stream of tokens and to convert it into a tree that represents the structure of the program. And once you have this parse tree, then it's very easy to do things with the program, like running it in an interpreter, or maybe compiling or transpiling it to some other language or machine code. So let's dive in. Tokenization. Well, first let me show you around the language. The language started out with the traditional print hello world. And as you can see, we have a bit of weird strings here. Strings always start with an underscore, indicating that this is a string, and they last until the next new line or white space. All of the underscores are actually white spaces, so they should be replaced. And the reason for this is to keep the tokenizer very simple. Then we are printing a number. Next we're doing some assignments. This is the assignment operator in this language. So we are assigning a string to the question variable, and next we're assigning to the favorite variable. But the thing we're assigning here is based on a built-in function called askInteger. AskInteger gets a question within a variable, which it will probably print out to the user and return an integer, which is ultimately stored in favorite. Next we're printing the value of favorite. And then we're doing some if-else comparisons. So if the favorite is 42, we're printing something, some string. And if it's greater than or smaller than, we're printing other values. That should be pretty easy to understand, I guess. So first, let's do some tokenization on this. So from within our Python file, we're opening the example file, and we're going to be reading through it line by line. So for a line in file, and for each line I would like to split it into words just based on the spaces. So I'll first need to strip off the new line character at the end of the line, and then I'll split it into words. There. Now these words are already mostly tokens. The only thing we need to add to this to obtain tokens is to do some conversions. We want the integers to be converted to actual Python integers, and we'd like to decode the weird underscore strings. Besides that, we would like to give each token a type. So we'll create a list of tokens, and this list will contain tuples, where the first value in the tuple is the type, and the second value in the tuple is always the value. So for instance, we could get a string saying hello world, or we could get an integer with some other value in it. There. So that's what we're trying to achieve here in this tokenizer. Let's see. So we're moving through the words for words in words, and well, first let's check that we don't have empty words. If the words is nothing, which can of course happen if there are two spaces beside each other, we should probably just skip this. There. Else, if the words, well, let's start with integers. That should be pretty simple. Is digit is the way we can check in Python that a string only contains numbers. So if that's the case, then it's an integer, and we'd like to add a token, an integer token, 2 tokens, and we're converting the string word to the integer. There. Next up, well, let's do the strings then. So if the first character of the word is an underscore, then it's a string. And what we need to do is strip off the first character using a string slice, and then replace all of the remaining underscores by spaces. So now we have the actual string, and we can add a token for it. So it's a string type token, and this is its value. Right. There we are. What else? Let's see. Yeah, so we have some special words. These are called keywords in a programming language. So that's if, else, and arguably also print and ask int. Although functions can also be seen kind of like variables. But in this case, let's pick them up as keywords. So our keywords are if, else, and print and ask int. If it's one of these, then we'll append it to our token list as a keywords. There. Else if, well, what else do we have in the language here? Yeah, so we have some arrows, this left arrow, and we have an equal sign, and we have a larger than sign. We could of course create separate token types for this, but that would pretty quickly become a bit much, because you'll probably add things to the language like this and like that, and I don't know what else. So instead of creating separate types for each of these, I'm just going to say these are operators. We'll need to do a check through all of the characters within the word. So if all of the characters in the word are are within our set of token characters, well, what can they be? Something like this, I guess. I think we're pretty far with this. If that's the case, if all of the letters are within this string, then it's a token, and we'll just add it as a token to, sorry, it's not a token, it's an operator. And we'll add it as an operator to the list of tokens. Okay. What do we have left? Well, our user variables, like question and favorite. So this can, well, let's do some checking as well. Else if, let's just see if it contains at least one A to Z letter. So if our words, if the uppercase doesn't match the lowercase, then we'll know that at least one of the letters A through Z are in the string, and then we'll say, okay, this is a variable. In all other cases, we're going to be saying invalid token, that's the token, and we'll just end the program with an error code. We'll probably also want to know where the end of each line is. So by the end of the line, I'm going to be inserting an additional symbol called EOL, end of line, and it doesn't have a value there. Well, let's make this a tuple. There we go. Okay. Well, if this works, then we should be getting a valid list of tokens now. Let's run it. Oh yeah, first try. Nice. So print is a keyword, str is hello world is a string, properly decoded. Nice. And then end of line. Yeah, this looks pretty well. The operators are recognized. Another operator here. Integers have been converted. Well, I'm pretty happy with this. So then we can move on to the actual parsing part. Um, Before we start writing that in Python, it's a good idea to create a grammar based on our example here. So let's do a split. A grammar basically is a set of production rules, as we call them, and we'll start from the top. So we start by specifying a complete program consists of, well, what does it consist of? We usually call these things statements. So a statement is the thing that a program does. Print is a statement. The assignment here is a statement. The entire if-else block is usually one statement. You could take the else apart, but things get really messy that way. So we'll call this a statement. But this, the part within the if-else block, is a statement as well. And this is a statement, and this is a statement. So many things can be statements. So basically we're saying here, a program is just a list of statements. And we express it this way, with the asterisk meaning 0 or more. Okay, so let's delve into the statement then. A statement can be, well, apparently it can be a print command. So it can be a print, but it can also be an assignment. This is also a statement. And we're using the pipe symbol as a choice. So a statement can be a print or it can be an assignment there. And of course the print and assignments we'll need to delve into these later on. What else can it be? Well, the else if else. Okay. Print. Well, it looks kind of like this. We have the literal value print, which is a keyword. But I'm not specifying the fact that it is a keyword, but it is. So we literally need to find the word print. And after that comes, yeah, well, a string. Okay, let's try. So it can be a string, or it can be an integer, or it can be, yeah, there. It can also be a variable reference. Okay, and probably it can be more things. We'll get back to this later on. For now, this will do. Moving on to the assignment. What does an assignment look like? So it starts with a variable. So this is also a class of array type of token. We're starting with a variable. Then we have the literal operator left arrow. And then there can be, well, a string, or there can be an ask int thingy. So probably it could also be numbers. So this sounds pretty similar to what we've done here. So we can of course copy paste it here, and then we can extend it. Let's say, okay, ask int should probably also be allowed. And then we'll probably want to allow it here as well. So we're seeing a bit of duplication here. We don't like that. So we need a name for this. This needs to be a production rule as well. And the traditional name for this is an expression. An expression in a programming language is basically everything that returns a value. So the expression can be a string, an integer, a variable reference, or the ask int function, built-in function call we have here. Alright, looking nice. So moving on to ask ints. Ask int, well, it's kind of like print, right? We have the literal function name, and then we have an expression which contains the thing to be printed. Based on these examples, we could also say it's just a string. That will work, at least for this simple example. But let's try to be as flexible as we can here. Oh no, it cannot just be a string, it at least needs to accept a variable. But let's be generic. It can be any expression, it will print the expression and then ask the user for an integer. Have we got everything? So a program has multiple statements. A statement can be print, it can be assignment, it can be if-else. A print can be accepts an expression. we've defined the expression here. An assignment also takes an expression, and the ask int, we've defined it here. Yes. Okay, the only thing left is the else if else. If else always starts out with an if, and then comes a condition. So in this case we only have this as a condition. So if we want to be really specific, which we probably don't want to, but it starts out with a variable, and then we have the is, and then we have which is an operator, and then we have a integer. This is a little bit too specific for my taste. We could make it very generic and say an operator is something like is an expression. But then we also would need to define expressions for things like equals and larger than, smaller than. We need to support booleans in our language, which we currently don't. So let's keep it a little simpler and say an if will always compare two expressions, and it can compare it with, well, in this case we only actually need the equals, but we can easily define some extra operators which we want to support. Something like this. Oh no, we're actually doing the larger than. Yeah, there. Okay. So this is a good start, I guess. And then there should be an else block. And oh no, sorry. First there is the right. Then there is a statement again after the condition. And in the examples we're seeing here, we're only getting one statement. So this is one statement. This is also one statement in the else block. And this is one statement. But probably it would be nicer to get a list of statements, right? So after the condition, this is the condition part. After the condition comes a list of statements. It can probably also be an empty list, I guess. Then comes the else. And then comes another list of statements. And then comes an end. We're not seeing it in this example, but usually if is also allowed without an else, right? So we should probably support that in our language as well. And I'm doing that by surrounding the else statements by parentheses and then adding a question mark to it. The question mark meaning this is optional. So this part comes 0 or 1 times. And then the end will always be there. Alright, very nice. I think we have the grammar now. So let's move on to actually implementing the recursive descent parser within Python. So what we want to achieve here is to convert the list of tokens that we've created above into some sort of tree structure that represents the structure of the program. So what would a tree like that look like? Well, so for instance, for the application we just created, the top level is always a program node, and we'll represent the nodes by tuples again, where the first item in the tuple is the name of the node, so program in this case, and then any further items in the tuple can be the extra data that's associated with that node. So in the case of a program, that would be the list of statements. So we start out with a statement next, and the first statement in our example program was actually a print statement. So print, and the print statement had a literal string hello world as an argument. So this is the literal lexical token hello world, and on the next statement would be a print 1 2 3. So that would be very similar. Let's just copy this here, and it would be an integer, I think 123, etc. So this is kind of the thing we want to achieve, and of course this gets more complicated the more language constructs we support. I'll comment this out for now because we want to produce this in code, of course. A recursive descent parser always starts at the main node type, which is the program, and then recursively moves downward from there. And there will be a function for each of these rules. So there will be a function parse program, and well, let's make all of the functions. So a parse statement, and a parse print, parse assignment, parse expression, parse ask int, there, and then there is a parse if else. And each of these parse functions will try to extract to take some of the first tokens in this list and to remove them from the list and to create a node from this. And this node can contain other parts of the can contain other nodes, that way creating a tree. If it doesn't manage to parse the thing it's meant to parse, say we're calling parse print, but the word print is not the first token in our list, then it will just return none, indicating there is no print here, try something else. So let's start by implementing the parse print function. The parse print function will look at the first token in the list, so this is the head of the list, and it will try to see if this token is actually a keyword, and the print keyword to be exact. If that's the case, then we're actually matching a print statement here. If that's not the case, then we'll just return none, meaning we didn't manage to parse a print, but you can maybe try other options. If there was a print, the word print here, then we can move on to the next token. So we're doing a pop 0, meaning we shift the entire list one position to the left. And then the next token that's currently at the head position, at position 0, should be, oh no, wait, we don't know what kind of token it is. It should be an expression, there. So at this point we should be parsing an expression, and we'll create a function for that. So we'll just call on the parse expression function, which we'll be implementing later, and it should give us a expression node back. If the parse expression doesn't manage to actually find an expression at that spot, for instance because somebody created a program and did this, then that's a problem, because then the parse expression should be returning none because it doesn't see an expression, it saw an end of line instead, and then the print would be invalid. So that's why the print should actually check if the expression that is returned is not actually none, because that would be an error. So the assertion will now just blow up the program and stop the parsing, and then you'll have to debug your mylang program. Error handling for this parser will be pretty bad. It doesn't tell you anything about which line number the error was, etc. So better write good programs. Now we have everything we need. So we know it's a print, and we now have a node for the expression. So we can now return a new node. It's a node of the type print, and as data it just has the expression node. And the expression node can be all kinds of things, right? We get to expression later, but it can be any of these terminal tokens, so lexical tokens, or it can be the ask int node. All right, let's move on to the expression then. Let's see what we can do here. So string, int, or var. Let's check if the token that's at the head, if its type is any of these. Is it actually a string or an integer, or a var. I just realized that. Yes, let's make these capitals. That makes it more consistent. This way we know that when we encounter capitals, then that's the type of a lexical token, and smaller letters are reserved for the rules, the production rules. Did I get them all? Yes. Oh, not completely all. End of line. There. So if the token type is either string or int or variable, well, that's these three cases, then we can just strictly speaking, we should be returning something like this. We say we are an expression, and our contents of the expression is just this token. We shouldn't forget, however, that we also need to remove the token from the list, and shift the rest of the list one position to the left. So we can do that with pop, and pop will also return the value of this token. So what we're actually returning here would be something that looks like this. It's an expression, and then there would be a token would be something like this. And that works, and that's manageable. But in this case, expression doesn't really do anything. It's just an extra layer. It doesn't have any functionality. So we can return it this way, but then we get a very deep tree with lots of things that don't really add anything of value. So we can just as well remove the expression part here, and just say we're returning the string or the int or the var token immediately. Okay, the other option for expression is an ask int. So if the token wasn't one of these, we can just call the ask int parse ask int function, and it will either well, it doesn't really matter. There are two cases. Either it manages to parse an ask int function call, in which case it will return a node for us, or it will return none. And basically that's also what we need to do. We either need to return whatever this thing returns, the node, or it needs to return none if it didn't find anything. So this works. So currently we have implemented expression like this. I'm quite curious to see if we can already parse a little bit. Usually you start parsing at the program, but we don't have that one implemented yet. So let's just start parsing at print. So parse print, and it should be able to work as the first line in our or the first couple of tokens actually do match a print. Let's see. Right, that doesn't do anything unless I actually print the output. It didn't crash though, that's good news. None. Okay, so that means it didn't match it. Interesting. How do we go about this? Oh, yeah, never mind, I already spotted it. I was going to say just put a breakpoint here and see what happens, but I think this will already fix this. Yeah, there. So there we have our first parse tree. Awesome. It's only a partial tree. This is not an actual program, because a program will always start with the program node here. But this is what a print looks like. Very nice. Let's see if we can move a little bit up to a statement. So what is a statement? A statement is either a print or an assignment or an if-else, followed by, I forgot to mention that, but the statement always ends with a new line. There. Okay, so that's what we need to do. So to see if it's a print, we just call the parse print method, and it will return as a node or it will return none. So if it's a node, then we're basically done. So we can of course do something like this. We say this is a statement, and then this is our data. But again, statement doesn't really add anything, so I might as well just return the node value. the statement production rule has no functionality in our language. It's basically just a combination of either of these things. And I do need, of course, to see if we do have a new line after the print. So if there's a node, we should from tokens pop the first token after the print, and its type should be end of line. So we assert that. If that's not the case, again the program will crash. And we're going to be doing that for all of these other things as well, which feels kind of repetitive, but let's do that first. So this would be parse assignment, and then parse if else. And if none of these match, well then we'll just have to return none, saying there are no further statements to be parsed at this point. We don't like repetition, so what we can do was perhaps something like this. If not node only, then we do this, and if there's still no node, then we do this. And this way we only have to do the assertion checking once. No? But there is even a better way. And that's making use of the logical OR in Python. It will always return the first of the OR parts that is not false-ish. So if parseInt returns a node, then that's what gets assigned to node. If it doesn't, if it returns none, only then will it try to run this function, and if that returns a node, then that will be assigned. If that returns none, parse if else will be run, and if that returns none, then none will actually be set to the node. So that's basically, yeah, that's exactly the same as we had before, only a lot shorter. Let's see if this works. So now we should be able to do parse statements. And of course, if it doesn't match a print, then it will try to do the assignments, which are not implemented yet. So these will never match. We'll get to that. Run it. Exactly. So we still get just the print node, because we decided for the statement not to add a node of itself, right? Because it would just be clutter. Well, which shall we do next? Maybe parse assignment then. What does an assignment look like? So we start out with a variable. So if tokens 0 equals, we just need to check the type of the head of the tokens. If it is a variable, then we should be able to move on to the if it's a variable, then the next thing should be a left arrow. The thing is, if we only see the variable, do we know this is going to be an assignment? Can we already consume this token, or do we need to look ahead a little bit further? And I'd say that's the safe thing to do. So we'll look at not the first token in the line of tokens, but the second, and we see if its value, if its actual string, matches this operator there. So if the first token in the list is a variable, and the second token is the left arrow, then we know that this will be an assignment. Let's see. So we'll pop the variable token to var, and we'll just pop the arrow function into nothingness. We don't care about it because it's always just an arrow. And after that comes an expression. So we just run parse expression. We've already implemented it there. So now we have everything we need. So So basically we should be able to now just return assignments, and it has two data arguments, a variable name and a token. Yeah, that looks pretty. And if it doesn't match something resembling an assignment, then we just return none. Oh, sorry, this shouldn't be token, this should be expression, of course, an expression node. Let's test that. In order to do that, we should modify the application a little bit, see if this works. And run it here. Yeah, an assignment, and it has a question, the variable question on the left side, and it has a string on the right side. Well, that's exactly it. Nice. Let's change the example back there. What else do we need to do? Maybe it's time now to start parsing the actual program. And parsing a program means repeating the parse statement function as often as it will go. So we'll call parse statements, and it should return the statement node, statement there. And if that's not the case, if it's returning none, then we should just end looping. If it is returning a statement, we should be adding this statement to a list, right? Because a program is just a list of statements. So we'll add it to the list. And then by the end, well, we should return our own node saying this is a program, and the program consists of these statements. Alright, let's see what happens. So now we can run parse program, and ooh, almost there. So apparently I'm not sure what's happening here. So we should be opening the debugger. Where is it? There. So what do we have? We have a node which is an assignment. And the assignment something went wrong with the assignment. You see that? The assignment doesn't have an expression. That's a problem. That is a problem. How can that be? So where's the parse assignment? Oh, right. So we forgot to check if the expression actually manages to parse. So there should be an assert here. Assert yet the expression is not none. Now we'll still get an error, but probably we'll get an error at a more sensible point in our program. Yes, so expression is not none, so it didn't manage to parse a favorite thing. Alright, yes, and that's because the askInt, the next token here in line is askInt, and we didn't implement that parse yet. But that is pretty cool, because that means that we've managed to parse our program already up to this point, which is pretty far along already. Nice. Now askInt should probably be very easy, as it's basically the same as our print implementation. It's just a different keyword, right? It's a keyword and then an expression. So I'll just go ahead and make a copy here and adapt it a little. Okay. And that only leaves us with the parse if else. Let's see if we can tackle that straight away. This is the longest we have, it's the most complex, but I think we'll manage. It starts with an if keyword. So if the token is a keyword that is if, well, actually, if it's not that, then we'll just return none, stating we didn't match anything. If it did, then we'll start by parsing an expression. And this is our left operand. And the operand should be there. It may not be none, otherwise we'll crash. Next comes the operator token. Operator. So we just pop the first token. And this token should be an operator. If the type of this token is not operator, then we'll crash. Next comes the right operand. It's the same as the left one. There. And after that comes statements. And coming to think of it, we're missing a little thingy here in our grammar, which is the new line. Right? Because if you look at the language example, we see after this part there's first a new line, and only then come these statements. And the statements themselves are terminated by new lines each. But we do need a new line here. So I've added it here, and the same applies to else. There. We don't need to put it after and, because the if-else is part of a statement itself, and the statement terminates with a new line there. So it's only for the else and for the if part. Okay, so let's just check if this is indeed an end of line, a new line. Let's not call that operator, sorry for the confusion. This is what we meant to do. So in a single line, we consume one token and we check that it's an end of line. Next comes a list of statements. And creating a list of statements is something we've already done before in the parse program. So we could be reusing this, except that we don't want the program node to be created, we just want a list. So I'll create a new function, parse list of statements, and it will just do all of this and return the list of statements. And then right here we say parse list of statements, and we're done. Okay, and then we can reuse that function here. So this is the well, what should we call it? The true statements. Statements is parse list of statements, and then comes the optional else. So if the current head token is the keyword else, then we need to consume another new line, end of line there, and after that comes a list of statements. Okay, so these will be the false statements to be executed if the condition evaluates to false. And that's already this block, this optional block. And then we move on to the AND, which should happen in both cases. So again, this is just consuming the token and verifying that it is a keyword that says AND. Okay, and if all of that happens, then we should be able to return a if-else node. And it has, well, we just provide everything as data, so the left and the operator and the right and the true statements and the false statements. What's possibly unbound? Oh yes, so if there are no false statements, well, you just set it to none, indicating there is no else condition. Okay, let's run it. Okay, so apparently we're going wrong in our if-else. So we need to have a look at the debugger again, and mostly I'm curious to see in the globals what's currently in tokens. Right, so I see the problem already. The first token is if, and we did check if there is an if, but we didn't consume the if token. So we need to remove it from the list. Well, 0. There, moving on to the next token. Run it again. What's the problem now? Operator 0 apparently. Oh, wrong way around. It should be an operator. And I've copy pasted that mistake a couple of times, so all of these should be true. Sorry about the confusion. This should okay. I think I managed to spot them all. Run again. Now what? So after the else, oh, same problem. Okay, systematic errors here. Just like with the if, I'm forgetting to consume the else. Right, so here we've checked that the token is an else, but then we need to actually remove it from the list. Otherwise, it will keep hanging on the else for all the rest. Yes, and I think we're at the end now. Let's see what happens in globals. Yes, tokens is empty. Which is actually very good news, because that means we've managed to parse everything up till the end. Only what happens now is that it will keep trying to parse, and then it will just read past the end of tokens. So we could be adding all kinds of checks to check for len tokens, etc. But a much easier way is to just add one special token at the very end of the list of tokens, and let's call it EOF for end of file, and it doesn't have any data attached to it. And this end of file token, it doesn't match anything, right? So what will happen is that the parse statements, it won't match any of these, so it will return from parse statements. Parse list of statements here. Return from parse list of statements, and then finally it will return a program. Now there is one extra check we should do. Now first let me run this and see if this actually works. Not quite yet. Why is that? Oh right. This should be an end, of course. So we're again reading past the input, and that's because we're reading ahead one token. So the token at 0 would be the end of file, and then it would try to see what token is after this. But we're quite lucky, because this causes us to spot the bug that was here. It should be an end, that's clear. I think now it will run. Yes, awesome. So we have our parse tree. It's a little hard to see. We probably want some fancy formatting for this to actually show it as a tree. But you can see that it actually does have some depth to it, going by the amount of closing brackets here. This is actually the result we were looking for. This is awesome. As I mentioned, there's one little thing we do need to fix, and that is what if there is something it cannot parse at the end of the program? So let's say we have an end token here, which doesn't make any sense, and there is no rule that matches this. Let's see what happens now. Yes, it's not complaining at all. It just stops to parse, and that is because within our parse program, we call the parse list of statements, and it just doesn't manage to match the parse statement to anything, right? Because AND is not something that you can start a statement with. So it will just stop the loop and just end the program. And now what we can do here is check that after we've read all of the statements, we can do a check if we're now at the end of file. So asserts tokens 0 0 equals end of file. And now if we run it, we should get an error here. Yes, this assertion, because this program is invalid. Go back, run it again, and you see that it does manage to parse it. I hope this gives you a very practical way of thinking about recursive descent parsers. There's not a lot of magic involved, it's just functions, quite a few functions if your program gets bigger. Try to keep them organized, give them good names, and you'll probably be fine.